Good evening, everyone, and welcome to the first AIP Line Starling Trimble public event of 2025. Thank you so much for coming out on this Friday evening, and thanks to everyone who might be watching the video, which we will post in a few days. I'm Will Thomas, the Spencer R. Wirt Director of Research in History, Policy, and Culture here at the American Institute of Physics, and our speaker tonight is Jaco de Swart, an AIP Robert H.G. Hellman postdoctoral fellow working at MIT. Before we properly introduce Jaco, I'd like to take a moment to note the sheer number of names that I've just mentioned, which reflects how important AIP's friends and donors are to what we do. This event series was endowed 12 years ago by the astronomer Virginia Trimble, in honor of her late father, Line Starling Trimble, a chemist. Jaco's fellowship is based on a highly generous bequest to AIP by the Dutch physicist Robert Hellman, who is eager to help young researchers from abroad work here in the United States. With all the recent developments here in Washington, taking every opportunity we can to reinforce the international spirit of science is more important than it's been in a long time. And I'd like to note that all of our history programs are in large part sustained through generous endowments, including my directorship and the directorship of our library and archives. If you'd like to contribute to the sustainment and expansion of our work, please head to our website, aip.org, and click Give to learn more. Finally, please do be aware that all attendees at tonight's event are obliged to abide by AIP's Code of Conduct, copies of which are available outside at the front desk and on our website. Suffice it here to say that AIP strives to foster an environment of the utmost professionalism and personal respect. With that, I'd like to turn things over to my esteemed colleague, Rebecca Charbonneau. Rebecca is an expert in the history of astronomy who joined our staff last summer after working as a Jansky Fellow at the National Radio Astronomy Observatory. And she will introduce Jaco.
Thank you. Good evening, everyone. So it is my pleasure to introduce our speaker, Dr. Jaco de Swart. Dr. de Swart has been working at MIT since 2022 as an AIP Robert H.G. Hellman postdoctoral fellow. And this fall, he will be taking up a Maria Skłodowska-Curie Actions postdoctoral fellowship at Cambridge University. Prior to his arrival at MIT, he received his PhD at the Institute of Physics at the University of Amsterdam and was a postdoctoral researcher at the Amsterdam School for Social Science Research. His research focuses on the history of dark matter, a topic that is also the subject of his forthcoming book under contract with MIT Press. You may have seen his work featured recently in Physics Today, where his article, 5 Decades of Missing Matter, was featured on the cover. Quite a high honor. Beyond his academic contributions, Dr. de Swart is passionate about science communication. He recently appeared in a PBS Nova documentary on dark energy and dark matter, bringing the mysteries of the cosmos to a wider audience. And if that weren't impressive enough, he also brings his talents to the stage as a bassist in the band X-Raiders. So please join me in giving a warm welcome to Dr. Jaco de Swart.
Thank you. Fabulous. Thank you very much for being here. And it's really a great honor to be here at the American Institute of Physics. And I would like to talk today about darkness, about probing darkness, trying to understand, to know the invisible. And that has been the most fundamental part of the astronomical sciences. That is, to probe and use our theories and use our equipment and technologies to try and understand the things that are hidden to our normal senses. Yet, our technologies have limits. And there are still some deep cosmic unknowns. And I will talk about one of them. Probably, or maybe the deepest and darkest of the unknowns, and depends who you ask, which is the problem of dark matter. That is, our current theories of the cosmos are saying that 85% of all the mass that exists in the universe consists of something that we've never seen before. It's dark. And this theory is deeply embedded in how we think about the structure and evolution of the universe. And physicists have come up on this idea of hidden mass existing in the universe through studying the dynamics of galaxies. That is looking at how galaxies rotate and looking at how galaxies move about in groups and clusters. And what they saw is that the velocity of these galaxies are so high, rapidly turning around, moving about in these groups, that they couldn't explain this movement by only the gravity of the visible mass. So there should be some extra stuff, some hidden stuff that adds some extra gravity to explain what's happening there. And all that's fine, but there's one thing left here which is an open question, and that is the most burning Nobel Prize worthy question in physics at the moment, and that is, what is this dark matter? And the hypothesis, the central hypothesis that that most physicists enjoy or support is that the dark matter is a new type of elementary particle, crisscrossing in the universe, billions of them, like an electron, but neutral, much tinier, much less heavy. And they call this the weakly interacting massive particle. At least that's the type of particle that has gained a lot of support. And this weakly interacting massive particle is also known as the WIMP. And the search for this WIMP, this weakly interacting massive particle, has been going on for quite a while, because indeed what it says, the particle is weakly interacting. So there's the tiniest chance that this particle might bump on some normal matter. And physicists have been trying to see if they can find traces of that, traces of this hypothetical particle. And there has been a huge infrastructure of detectors trying to find signs of this dark matter. There are detectors up at the International Space Station. There are detectors that people have built in the ice in the Antarctic to see if they can find any signs that might support evidence for dark matter. And there have been detectors deep underground in mountains and in old mines to see if they can find signs of dark matter. And this is an image of the xenon experiment, where they have a lot of xenon, the element, in a giant vat, where they hope that there is if the WIMP exists, it might have a nuclear recoil on one of these atoms. The atom shakes a bit, gives us a flash, and then they can see if this dark matter exists. If not, the WIMP will exist. But there's one thing happening here, and that is they have not yet found any evidence for the WIMP. There's only been null results. And that makes that some physicists, some dark matter physicists, have been getting away from this idea of the WIMP, or at least poking around what is going on and how should we be thinking about dark matter after 40 years of null results. So you have some physicists, this is in a paper in Nature, talk about the possibility that this natural WIMP may have been nothing more than an attractive red herring. And while there's still very good reasons to search for this WIMP, the fact that it hasn't been found does make that a lot of people are currently wondering how to move forward. And some physicists will say, maybe we're even in a little bit of a crisis. Where to move from here? Where to go from here? But I like to ask a prior question in a time of crisis. And sometimes when you are in a time of crisis, for example, when a certain political system is forming that seems highly problematic and has some similarities with other highly problematic political systems, you might ask, how do we get here? And that's quite a relevant question, if you ask me. For me, I ask this question in the case of dark matter. Where did this problem come from? And another way of phrasing it is, how did dark matter come to matter? What were the conditions, the historical conditions under which this problem started to strike root? Why did people start to care about this problem in the first place? And this has to do, and I have worked on this for a while now, this has to do, for example, with the development of cosmology, with the space race in the 60s and in the 1970s, and new ways of looking at the universe. And this has been part of my research. This is what I do as an American Institute of Physics Halleman Fellow, trying to look into where this problem of dark matter came from, and to see if it can help us think about where we are and how that happened in our search for dark matter. And I've been very lucky that I indeed have been able to sign a book contract for this project and working on the history of dark matter. And that is all because of this amazing fellowship that I'm on, the Helleman Fellowship, which I'm very, very grateful for, to be at MIT and working on this project. And what would I like to do for the rest of the time that I'm here is to give you a little snippet of what I am currently working on. So I've worked on several episodes in the history of dark matter, and I'm going to give you some new material. I hope this is going to be nice, and you will like this story that I'm patching together, and everything that you can give me in terms of feedback is very welcome. And this is the story of the WIMP. Where did the WIMP paradigm come from? And how can we understand that? And particularly, how can we understand that it was so successful and that people quite immediately started to take for granted that the dark matter is a new type of particle? And that's something that we're still dealing with today, that the obviousness that dark matter is a particle. There are very good reasons for it, very good scientific reasons for it. But there's something more to this history that helps us understand and explain why that was the case around the early 1980s, that this WIMP was so deeply settled in our thinking about the universe. And this question has become a little bit more urgent in the last couple of months. And that's because some of the detectors that are trying to find dark matter, trying to find the WIMP, one of them, the xenon experiment that I just mentioned, they have found what they call the neutrino fog. And this neutrino fog are the first signs of neutrinos from nuclear reactions in the sun coming in these experiments. And that's quite an exciting result, that you can find these neutrinos in these experiments, but it's also something that has been dreaded by some researchers for a while, because these neutrinos act as a fog, or at least they can act as a certain fog. There are so many of these neutrinos that they can overwhelm the detector. And the signals of these neutrinos bumping into the xenon look quite a bit like that of what you expect a WIMP would do. So there's a fog that can descend over this detector, making that it will be quite hard, if not impossible, to find the WIMP in these detectors. Which makes that the question has come up more often to think about where to go from here. Should we build yet another big detector? And this, I think, again, emphasizes the question, what gave rise to the WIMP paradigm? Why are we at the situation that we are, and can it help us to think about where to move from here? And what I would like to show, actually, in some irony of history, that it was actually the neutrino that helped to give rise to the WIMP paradigm in the first place. It was the neutrino, and I see this is quite small, but I can also tell you what's stated on there. The neutrino was the first dark matter candidate that came up. The neutrino opened the ways to think anew about what cosmology meant in the first place. That cosmology was a thing that wasn't just about stars, but also about particles. And neutrinos helped to give birth and give rise to this field now called particle cosmology. And thirdly, for a short amount of time, neutrinos were the dark matter. They solved everything. And that's something that I would like to tell you about. How the neutrino, now perhaps the reason for the demise of the WIMP paradigm, or at least something that for some people is problematic, was also the origin of how people started to think about dark matter as a particle and the WIMP in particular. And that's what I'll do for the rest of this talk. And first, I will give you a little primer about how this problem of dark matter started to strike root in the early 1970s, which at that point was still called the problem of missing mass. And in the early 1970s, we have to think about the fact that the Big Bang Theory was just being accepted. The cosmic microwave background, the first light of the universe, was discovered in 1965, and by 1970, people started to be convinced that the Big Bang Theory was the theory of how to explain the expansion of the universe and the origin of the universe. And with that came a couple of questions, new questions to ask, or questions that became more important. And one of them was, what is the mass of the universe? Because if you know the mass of the universe, you could know whether the universe would expand forever or whether there's enough gravity for the universe to at one point stop expanding and maybe collapsing again. So the mass of the universe became a very central quantity people were interested in, which gave rise to questions about where is all the mass? How can we measure it? And indeed, I've written about this quite recently for Physics Today, which is this paper called 5 Decades of Missing Mass. 1974 was, a couple of months ago, was 50 years ago. Now it's 51 years ago. And that is what happened in 1974, that there were 2 sets of cosmologists, one group in Princeton and one group in Estonia, that started to think about these questions. And they started to notice that there was something in the measurements of rotations of galaxies and the measure of mass it gave for these galaxies and the dynamics of clusters, so how galaxies move in clusters, that said something about the mass of galaxies. And what they showed is what you see in this little diagram here, which shows the mass on the y-axis and the radius on the x-axis, where you see that the further you go out from a galaxy, the mass keeps on increasing, even after where all the visible mass stops. You see that there's more and more and more and more mass. And that's why they said galaxies are actually 10 times heavier, more massive than we have thought before. And there should be something missing. There is something missing, and there should be missing mass out there. And that's what these authors showed in 1974. And this result wasn't immediately accepted. It took quite a while for people to be convinced that this was the case, and it took at least until 1979, in which a big review paper was written that put together new data that was collected by astronomers like Vera Rubin. Vera Rubin, who worked on the rotation of galaxies. This is not Vera Rubin. On the rotation of galaxies. The paper that was written was actually a summer student of Vera Rubin. This is going too fast. Come on. Which was Sandy Faber. Sandy Faber was a summer student with Vera Rubin, and she wrote a very important review on the masses of galaxies, showing that hidden mass or missing mass should and must exist in the universe. And this was in 1979. But there wasn't a lot of talk about what this stuff was, even in this review paper, and especially not by the group in Princeton, who was led by Jerry Stryker and with Jim Peebles also involved, now a famous cosmologist who recently won the Nobel Prize. And when I chatted with Jim Peebles, he said the following about that time, is that the results evident then didn't excite me at all. It was obvious that we don't understand mass, and it's obvious that there was a lot of work to be done to understand it better. So he moved on to work on a different problem. This was the state of astronomy in the early 1970s, was there's a lot of stuff we don't know. I'm not sure what this missing mass means, but let's move on and try to get a more complete picture of what the universe actually looks like. And that was what a lot of cosmologists did. So this was a thing that ended up at the sideline for many people. But in the dark, hidden corners of physics, some people did start to care and start to think about what this was mean and how you could solve this problem. And particularly, thinking about it as neutrinos. No. Also not. Yes. And one of them was Ramanath Kaushik, who grew up in India and was based at the Tata Institute for Fundamental Research, where he worked on cosmic rays for his PhD. That is, particles that are coming from the sky and might hit us here on Earth and will tell us something about the processes that are happening in the universe. And while working on cosmic rays, Kaushik got very interested in neutrinos. And neutrinos were this particle that was hypothesized by Wolfgang Pauli in 1930, and it was shown to exist in the 50s. It was detected in the 50s. The neutrino was something that was on the radar for a lot of people that were doing particle physicists, and especially for Kaushik. And he got made fun of because he really liked neutrinos in his PhD. And this is at the Tata Institute in Mumbai. This is what he said. Everybody used to make fun of me because of my interest in neutrinos, and they would always say that if there was a problem, they would say that I would solve it with neutrinos. He said when I interviewed him. And that is what happened at one point. It happened when he moved to Berkeley. He gave a talk at a conference where a Berkeley astronomer was, who immediately invited him to come over to Berkeley to teach in Berkeley, and that was in 1970. And in 1970, he moved to Berkeley to teach there, and that's where he also learned more about cosmology. Berkeley was had a big group in astronomy, and he learned cosmology from a new book that came out from Jim Peebles. And he learned about the missing mass problem and the problem in groups and clusters of galaxies, that these galaxies and clusters are moving way too fast. And he had an idea. That was to use neutrinos to solve this problem. So he wrote 2 papers with a graduate student that happened to enter his room, and he said, "You shouldn't do a project with me. I'm just a teacher. I don't have money." But the graduate student stayed, and they wrote 2 papers about neutrinos together, and particularly using cosmology and the things that he learned from Peebles' book to think about what the neutrino is. And see if you can read that with me. The first paper he wrote in 1972 was called An Upper Limit on the Neutrino Rest Mass. So he used the idea of neutrinos coming out of the early thermodynamics of the Big Bang. The Big Bang has created photons, but also created neutrinos in the moment of expansion, and he was well aware of that. But then he learned about the fact that there was data available on the mass of the universe, which was in the early 1970s. So he used the data on the mass of the universe and calculations on how many neutrinos there should be in the universe to put a limit on what this neutrino might weigh. A second paper he wrote was that the gravity of these neutrinos, they say, could help understand the virial mass discrepancy in the coma cluster. The neutrinos could be the hidden mass. And there was another person that did quite similar, also on the edges and the fringes of physics at the time, did something quite similar. And that was Alex Zalai. And he was a PhD student in Hungary, in Budapest, where he learned particle physics from his parents who worked in the lab. He said to me that he quite literally grew up in the physics lab because his parents' house was located next to the physics lab. And that's where he grew up. And his mentor gave him a paper by Yakov Zeldovich, a Russian physicist, who had shown that if there's a cosmic microwave background of light particles, then there should also be a cosmic neutrino background. And his advisor said, do these calculations better. So he also learned from Jim Peebles about cosmology, about the Big Bang, and about using the Big Bang and using those theories to put a limit, you see here, on the neutrino rest mass from cosmology. And he too says the missing mass in these clusters of galaxies may be explained by the relict cosmological neutrinos produced in the hot era following the Big Bang. That's what it says. You have to believe me that that's what it says. Alex Zalai talked about this at a conference in 1972 at Lake Balaton in Hungary. And that was the big neutrino conference. And it had a lot of fancy people visit. And here you see some of them, but you can't really see it too well. But it had Feynman also visiting there. And being a young PhD student, Alex Zalai went up to him after he gave his talk. So Alex Zalai gave a tiny talk. And he asked him to sign his Feynman lectures, which is what you see here, which is very cute. And it says the following: "Dear Alex, thank you for your hospitality and your help at, I think that's Lake Balaton. I won't forget my visit. I was surprised to learn that neutrino mass could be limited by thoughts of cosmology. Richard Feynman." And I find this interesting because he says thoughts of cosmology, and actually Richard Feynman was kind of a bit of a skeptic of the science of cosmology, and that could actually be a science. And I think that is something that they definitely experienced, and especially Alex Zalai experienced that. He said that what he was doing was slightly crazy, especially particle physicists found it slightly crazy. This is what he said: "If everybody thinks this is crazy, I have to do something more tangible if I want to stay in physics." And he had something tangible to do. It wasn't in physics. Actually, Alex Zalai was thinking of quitting physics to take up his career being a guitar player in Pantaray, which was an experimental progressive rock band in Hungary. And I emailed Alex because he is now a professor at Johns Hopkins. And I emailed him, we chatted, and I interviewed him a while back, and I emailed him if he could be here. And he said, "I'm so sorry I can't be here because I'm flying to Hungary to play the very last show ever of Pantaray." So he's playing the show this weekend there. Yeah. Ramanath Kaushik also had a similar experience. In an interview, he said to me that there was no reception to this paper that he wrote about neutrinos being this missing mass. Nobody bothered about it. And that stayed for a while until there were some fundamental changes in particle physics, that people started to care about these things. There was a big revolution in particle physics that some of you may know about, have heard about, have read about. There has been amazing literature about, amazing research about this by some very influential authors on what happened in the 1970s in particle physics, because it was the birth of what we now call the standard model of particle physics. We found out in 1970 through about the weak neutral currents, which showed that the weak force and the electromagnetic force could be unified in one account. In 1974, we found new particles. We found the J-psi particle at Stanford that showed that quarks must exist and that there's a new family of quarks that made that slowly but surely a very new way of thinking of particle physics came about, and that is what we now call the standard model of particle physics. And every month there would be a new analysis or a new discovery with the big detectors and accelerators that were built around the world. That gave us eventually this quite familiar diagram that says that we have these families of quarks, and then we have three generations G families of matter: the electron, the muon, and these electrons and muon, they have a partner, which is the neutrino. They come with a neutrino. And this is what settled down in the 1970s. And I want to focus on this third family because that's what happened in 1977. This is the Spear accelerator in Stanford, built on a parking lot, where they found evidence of the tau particle in 1977. So this was a new particle, a new lepton, they called this, from this family of leptons, the tau particle. And the tau particle was very influential as discovery, but for a lot of people it also meant that there might be another neutrino, a tau neutrino, so that the family of neutrino now also got expanded. There used to be 2, now there were 3. 3 neutrinos. At least it wasn't proven yet, but most physicists assumed there was a 3rd neutrino. Could there be a 4th neutrino? Was there yet another family of neutrinos? How would we know? How do we know how many families of neutrinos and how many families of leptons could exist? This was a question that people started to ask in 1977, and this interest was backed by a new type of theory that was developing, that we now know as grand unified theories. And that was a theory that could unify in one system the different forces, the electromagnetic force, the weak force, the strong force, together. And many of these ideas to unify these forces involved other particles. And they also involved neutrinos to have mass. And that's the thing I didn't tell you about. But for a long time, the neutrino was mostly thought to be massless, a massless particle. And that's part of the reason also why the results of Kaushik and Szalai were not picked up, which is why should the neutrino have mass? So the grand unified theories added a new dimension to thinking about new particles and particles that are massive. But then the question remained, how many of them exist? And in 1977, there's this burst. There's this burst of physicists thinking about how to limit the amount of neutrinos that could exist. So you see a set of papers that came out all in 1977. A Dutch one, an American one, a Japanese paper, and a Russian group. They all did the same. What they did is to put limits on the masses and number of neutral weakly interacting particles. Some people called them heavy leptons or heavy neutrinos. How many of these heavy neutrinos are there? And how can we understand that? All these people started to use cosmology, started to use the Big Bang Theory, by then something that people started to take for granted, started to use that to put limits on these particles. And that had to do with, if you know how the thermodynamics of this expanding plasma of particles in the beginning of the universe works, then you can calculate how many of these particles are created. And if you know what the mass of the universe is, then you can say they can be more massive than a certain amount. And that's what all these collaborations did. One of them was a paper written by Steven Weinberg, co-authored by Steven Weinberg, who in 1977 also published this famous book. Has somebody seen this book before? One person? Ah, come on, there's another person, right? Okay. The First 3 Minutes, which indeed was a new expose on how to think about the Big Bang in terms of particles and the thermodynamics in the early universe. And this way of thinking started to really settle down in the late 1970s. And this way of thinking, by which I mean using cosmology to constrain particle physics. And this is a paper from Dave Schramm and Mike Turner in Physics Today in 1979. The early universe is the poor man's high-energy physics laboratory. Knowledge about its state can be deducted from current observations and can illuminate our knowledge of the fundamental interactions. This indeed can be seen as part of the birth of particle cosmology, using cosmology to constrain particle physics. And this also meant that people started to look the other way around. What can particle physics say about cosmology? And quite soon a paper came out in 1978 where particle physicists and astronomers joined together to think about heavy neutrinos as the ideal material from which to form the missing mass. And it became quite obvious for some of these people, but the real case for neutrinos, for heavy neutrinos, as the missing mass happened in 1980. In 1980, there was actually experimental evidence for a massive neutrino. 2 experiments showed that the neutrino should have mass. And this was widely influential. This really made the field explode. And one of these observations was done by Frederick Rhines. This person, who was also the person who detected the neutrino in the 1950s. He was the person to prove that the neutrino exists, and he got the Nobel Prize for that in the 1990s. And in 1980, he came out with a new result. And this result was saying, he was quite pompously talking and introducing his result at the APS meeting in 1980, showing that neutrinos oscillate. That is what he showed. He said neutrinos have to oscillate between the different families, from the muon neutrino to the electron neutrino and tau neutrino. They all oscillate in between each other. And if that's the case, they need to have mass. Hey. So this institute called the AIP sent around this news release. The highlight for immediate release was from the American Physical Society meeting that neutrinos oscillate. That it says here in the bottom, let's see if I can find that, that it was long thought to be a massless particle traveling at the speed of light, but they now have mass, and that they oscillate among each of several types of neutrinos. And now the last sentence, such a development could have a large impact not only on theories of particle physics, but on theories of cosmology as well. And this hit as a bomb. And this bomb was made even bigger by a result a month later, 2 months later. A Russian experiment measuring the mass of the neutrino came out with an observation that they had exactly measured the mass. They said the neutrino is about 30 electron volts. This is about 100,000th of the mass of the electron. And this mass was exactly the mass that Kaushik and Zalai had deduced from their arguments, almost 10 years before that. So in 1980, what you see is an enormous explosion in interest in this problem and in particle cosmology, thinking about the universe in terms of particles. For one thing, Alex Zalai said he suddenly got 2 postdoctoral offers after trying to see if he could quit the field because he didn't really know if he could stay in academia. And he got offers in Berkeley and at Fermilab. And when I interviewed Jim Peebles about this event, he said, this opened the floodgate. The measurement of the neutrino, what you see here is the amount of citations for one of these papers that happened quite immediately, opened the floodgate to think about dark matter as a particle. These are 5 papers that came out quite immediately, talking about what by then starts to be known as the neutrino-dominated universe. Neutrino-dominated universe, massive neutrinos in the large-scale structure of the universe, cosmological impact of the neutrino rest mass. These are all papers because people found that the neutrino would have mass. And all these papers did something quite special, because they started to think about neutrinos and the Big Bang, and also how neutrinos would help form galaxies, which was still an open question in astronomy and cosmology, how galaxies are shaped and formed. And thinking about the neutrino, having a massive neutrino in the beginning of the universe would help to form primeval fluctuations, primordial fluctuations, fluctuations in the mass. So let me try if I can explain that using a diagram from around that time. But first sum up all the things that the neutrino was explaining at the time. This neutrino-dominated universe, of course, explained the missing mass problem, because the neutrino would have mass and it could explain why galaxies are moving the way they do. It could explain a different problem, which was called the missing solar neutrino problem, which I will not talk about now, but was a problem about measuring the neutrinos coming from the sun. And there was an issue there, and it could solve this issue. Then there was another one, and that if you add neutrinos to the mass of the universe might just be massive enough to be of critical density. And that is the amount of mass that you need for the expansion of the universe to slow down and stop at one point. And if you add a little bit more mass, what could happen is that the universe might contract. And the neutrino could help make the universe critical density. And this became a very important argument a year later when people started to talk about inflation, which gave another reason to think about the universe being of this density. And then indeed, well, like I said, the neutrino would explain the formation of galaxies. And how that will happen is if you look at this little diagram where you see the time starting here from the Big Bang and the universe evolving this way. People started to set up these little diagrams where you see this hot plasma evolving from a very early epoch into what's called the grand unified theory scale of energies into the present, and slowly but surely forming atoms, forming helium and deuterium, also the decoupling of gamma, those are the photons, so that's the cosmic microwave background that happened. And at one point also you would have the decoupling of neutrinos. And what all these papers were showing was that the neutrinos would decouple before normal matter would form. So these neutrinos started to move freely from this plasma, the hot plasma of the Big Bang. So the neutrinos could start to form these early seeds, the early seeds of little lumpy matter, where it is a little bit more matter and where there's a little bit less matter. And that will be determined by the distribution of the neutrinos. The neutrinos would form a way to think about how the primordial fluctuations of the universe formed and eventually would form galaxies. And it was quite attractive. One of the groups, including Zeldovich and Alex Zalai, would say that cosmology with massive neutrinos is so attractive that, to paraphrase Voltaire, if it did not exist, it would be necessary to invent it. And Zeldovich was particularly interested in the neutrino scenario, the neutrino-dominated universe, because it gave evidence for his theory of how structure would form. These neutrinos, because of the way they move and decouple before normal matter starts to form, they determine on what scale the universe starts to form mass for the first time. So is that on the galaxy scale? Is that on a bigger scale? How big are the first lumps in the universe? That's how you could see that. That's what the neutrino would determine. And if you followed the neutrino, the first lumps of the universe were the size of clusters of galaxies. And from these clusters, galaxies would form. And that's where you get this picture of galaxy formation. You have this hump of homogeneous mass, almost homogeneous, but on the scale of clusters of galaxies, the first mass lumps start to create. And that was his picture. And that's why he was such a fan of the neutrino. But it wasn't only scientists who were interested in this. It exploded in the science news, this idea of the neutrino. So you see in every publication people mentioning the neutrinos. Signature of the missing mass. Neutrinos to iron out cosmic problem. Massive neutrinos, masters of the universe. Neutrinos at mass would explain a lot about the distribution and dynamics of galaxies. They might even suffice to close the universe. Closing the universe was to make the universe critical density. Ups and downs of neutrino oscillations, neutrino weight watching, written by recent Nobel Prize laureate at that moment, Sheldon Glashow, who was a fan of this idea, and also the nuclear evidence that neutrinos have mass. Who from you is from Pennsylvania? Well, are you familiar with Reading, Pennsylvania? Is that how you pronounce it? Yeah. Okay. This is from the Reading Eagle. The Reading piece written by a person called Virginia Payette, and she writes the following about the neutrinos. As if we didn't have enough to worry about, like trying to decide who's likely to mess up the world faster, Jimmy Carter or Ronald Reagan, we now have a new problem, the neutrino, which was about the mass of the neutrino and the fact that it might mean that the universe will collapse again at one point. And this was also something that Isaac Asimov wrote about in a science fiction journal. He wrote about the neutrino and the collapsible universe, wherein the wily neutrino tries to tame the expanding universe. It was a big hit. The neutrino-dominated universe was an enormous hit in thinking about how the universe developed. And then at the same time, it was one of the key things that helped to think about a universe that needs to be studied using particle physics. And there were other things that were happening around the time. I already mentioned inflation. People were thinking about proton decay. People were thinking about the baryon asymmetry in the universe. These were all things that were irrelevant. But the neutrino-dominated universe was a very real connection between the early universe and all the particles that existed, and how and why the universe looks the way it looks. And that was fundamental to thinking and advertising this new way of doing cosmology, which was particle cosmology.
Just so you know, we have to wrap up around 7:30.
Yeah. This you saw in other things too. The Fermilab had the first astrophysics division at a national lab. So NASA funded the first particle astrophysics group. This was headed by Rocky Kolb and Mike Turner. Is somebody familiar with Michael Turner? This is I was interviewing him a couple of weeks ago, and then he gave me this picture. The first conferences came about. The first conferences dedicated to particle cosmology were organized. This is from 1983 to really share this new picture of the universe. And there were literally pictures. There were new pictures of the universe that were showing this complete history of the universe, starting with the quantum gravity epoch, going out, having the wild neutrinos coming out, to where we are now. And this was a thing made by Michael Turner for Discover magazine. And this is an era where these types of diagrams started to come out for the first time. This is another one from Joel Primack, and maybe some people have seen this before, where you have the cosmic Ouroboros, where the tiniest scales are connected to the largest scales. And indeed, dark matter plays a very big role in doing that. And this one is from 1984. But the neutrino was short-lived. By 1983, the neutrino dominated, and the universe was no more. And that had two reasons. One was that the experiment turned out to be the experimental result from the neutrino experiment of Frederick Rines turned out to be false. The statistics were done wrong. Richard Feynman had written a very scathing response, sent it out, never published. But it made so that when I was going through Frederick Rines' archive, The talk that he gave at the APS meeting in 1980, he came back to this talk where he announced this result in 1982, where he wrote, "Too bad this talk was ever given." Poor guy. Yeah, so that didn't stay up, and also the Russian experiment was never corroborated. So it was never falsified, but was also never shown to be true. And then in 1983, you also had something that happened with the help of this thing, which was a 64 megabyte computer. That helped to show and do the first simulation of the neutrino-dominated universe. And this simulation showed that, as it says in the last sentence, the conventional neutrino-dominated picture appears to be ruled out. It's funny it says conventional neutrino-dominated picture, because by then, in 1983, it was already the way of thinking about the universe. Neutrinos were hot. Neutrinos were moving very fast in the early universe, and the neutrinos, as the base of the successful model, needed to be tweaked. And instead of moving very fast, they needed to move slower, it appears. Instead of being hot in the Earth universe, the particles needed to be cold. And by 1984, this was shown to be the way to think about dark matter and particle dark matter, that the formation of galaxies in large-scale structure was done with cold dark matter. A very important review, again, partially done by Sandy Faber, and also by Joel Primack, who was one of the first to suggest that supersymmetry might play a role. Supersymmetry was a grand unified theory that had a lot of ideas about new particles that could exist. And these new particles could be this cold dark matter. Then in 1985, we again have Michael Turner writing for the first time about these weakly interacting massive particles as WIMPs. The WIMPs became part of the story, and quite soon this was the way that people started to think about that. This is a beautiful diagram that Mike Turner drew for the first conference ever on dark matter that happened in Princeton in 1985. And you have to think, so I think Return of the Jedi came out in 1983. So this was the way to think about that. The dark matter candidates, the very exotic candidates not listed. And here were all the different WIMPs. The invisible axion, the light neutrino, the photino, these were the supersymmetry particles. And this was the whole SUSY zoo, the supersymmetry zoo of particles that could exist in physics theory and could explain the dark matter. It became one of the hottest issues in cosmology, according to a Sky telescope. And it was really the neutrino that determined what was the standard of explanation, what needed to be explained for dark matter to have a convincing solution. And that is structure formation. You needed to make sense of how the universe formed structure using particle physics. And that also meant that some alternatives started to not get addressed at all. And one of these alternatives was thinking about an alternative law of gravity, which was introduced by Moti Milgram in 1983. And talking about this, Joel Primack says something very enlightening and clarifies how people thought about the time. So it's not at all clear what sort of particle physics could lead to a force law like Milgram's. The way he was analyzing what is good and what is bad theory is through whether it's good particle physics. And indeed, adjusting the force law of Newton is not good particle physics. It's not really part of particle physics at all. So it was particle physics that started to dominate what it means to do a good thing in cosmology and whatnot. This you have to wait for a bit. This is actually the first dark matter experiment that started to happen, which was originally a neutrino experiment. So the WIMPs were very, very successful also because the technology already existed to find and do the experiments to find them, which was the technology from neutrino experiments. But if you want to learn more about that, then you'll have to buy my book eventually. So this is what I wanted to say here, is that the WIMP rose from the ashes of the neutrino-dominated universe. And that is to say that the neutrino-dominated universe determined what the explanation, what needed explanation. It has such a huge explanatory power that is what the new theories had to simulate, at least. It was the first coherent theory of how structure in the universe formed, the first paradigm in cosmology, if you want to call it. We now call it the cold dark matter paradigm in cosmology. And it set standards. It set the standards for what is a good cosmological theory and what is not. And that's how we came about with this WIMP paradigm. So going forward, asking a question, and this is my last point, asking a question that resembles a question of a speaker that will come later in the season, Peter Gallison, is how do theories end? How do we think about where to go with the WIMP from here? Will it end or will it not? And I think what is relevant to think about is that it's not just about the WIMP that is at stake here, but it's about a way of doing and thinking about cosmology per se. That cosmology is about particles and about particle physics, and that these two are so deeply intertwined that is what's at stake if you want to go on with the WIMP, or you might want to leave it behind. Thank you very much.
Thank you so much for that talk. I think we have time for one or two questions from the audience. Wait for, I'll ask you to speak into the microphone so we get it on record.
This may be too technical for the audience, but you can deform it into something appropriate. But I was surprised that you didn't mention the WIMP miracle, which in my experience as an observer, as a spectator in the field, played an important role in what happened after the neutrinos fell. So could you comment on that?
Yeah. And that has to, well, would you agree with me that the neutrinos were the first WIMP miracle? In a sense that neutrinos had the right type of interaction to help form structure. So it's interesting what you say, because I have the feeling that the WIMP miracle is a type of argument that came only later, that people started to talk about only in the 90s, being that the weak interaction force is just the right that the right interaction that you want to have to explain why the density fluctuations are the way that they are. And I would love to hear about any ways that you've heard people talk about this miracle, but the people that I've interviewed thought this was a reconstruction that people said later, as that if you want a WIMP, the WIMP miracle is how you defend the WIMP to exist, but not something that people were talking about in the mid 80s. But maybe you have a different experience of that. But we can chat a little bit later about that. But it's a very good question.
We can take one more.
There was one over.
Someone, where am I not looking? Oh, there. Thank you. Oh.
Here in the front here.
Oh, good grief. So sorry.
So you said that the interactions that you were seeing with neutrinos far underground with the xenon is what you would be expecting from dark matter for the WIMPs. What goes into that? Why is that what you would expect?
Are you talking about the fact that it's hard to distinguish?
What makes it a fog?
That's a very good question. There's actually an expert sitting right next to you who probably knows how to answer that question a little bit better. But I'm not sure if that's the moment. This is the moment to talk about that, or you can talk about that a little bit later. You want to use this time for that? I'm looking at Rebecca. Or do you want to have one final?
I want to later here.
The time we set up.
Yeah, let's leave that for.
Well, I mean, we have an expert.
Okay, let's
Please.
So solar neutrinos can scatter off of the xenon target that's used for WIMP searches, and they'll cause the xenon target to recoil. It turns out, through a coincidence, if the WIMP particle mass happens to be a particular number, which is 6 GeV, it's about 6 proton masses, turns out the recoil energy spectrum, which is what the experiment can measure, would happen to look identical to that of solar neutrinos scattering off xenon atoms. So there's this one particular WIMP mass, if the WIMP existed with that mass, where the energy spectrum of the recoils would look precisely the same between solar neutrinos and that WIMP. So there's that one special mass where that's an issue. In general, WIMP experiments are looking at masses much higher, many orders of magnitude higher, but there is this one very light WIMP mass, which is about 6 proton masses, where through happenstance, the recoil energy spectrum would look identical, and you would not be able to tell whether it was a solar neutrino or a WIMP simply by looking at the data of the experiment itself. You'd have to look for an excess of events on top of the solar neutrino signals because we can't turn the solar neutrinos off.
Thanks.
And I think with that, we're at the end of our time. If you have any more questions, feel free to approach Jaco at the end of the...
Thanks very much, Rebecca. Thank you very much, Jaco. So we have 2 more talks coming up this spring. They're both going to be on Fridays. And the first Friday in May 2nd, we have Tiffany Nichols from Northeastern University, who is going to be talking about the LIGO experiment and why its detectors are sited in the places that they are. And then on May 30th, as Jaco alluded to, we have Peter Gallison coming to us from Harvard University, who's going to be talking about the role of history and philosophy of science in the Black Hole Initiative that they are running up there. And that's going to be, I think, a very exciting time as well. So I hope you'll be able to join us, and you can check out all of our lectures on our YouTube channel, which is AIP History. So thanks very much, everyone. Thank you very much, Jaco.
Thanks.